Okay, hello all. Thanks for coming to this edition of the ICTS string seminars by Zoom. Today we are happy to have Suvrat Raju with us, and he's going to talk about the holographic nature of null infinity. Over to Suvrat.
Okay, so thank you very much, Siddharth. Thank you all of you for showing up. I know many of you also at the morning long seminar, so thank you once again for coming for this one as well. So the work I'm going to talk about actually goes back to some papers I wrote, including some papers I wrote a few years ago with Shovik, Jan, and Kyriakos. And then, but I'm mostly going to talk about this most recent paper that I wrote with Alok, Siddharth, and Pushkar. So let me just start by telling you the main message that I hope to convey in this talk. So this talk is essentially about how we feel quantum information is localized in quantum gravity. And the kind of picture I'm going to try and establish in this talk is the following. The statement is that in a theory of quantum gravity, if you specify the wave function of the universe everywhere outside a bounded region, then I'm going to try and claim that you also specify it completely inside that region. Now this, I want to emphasize, is a very unusual property because it would certainly be false in a local quantum field theory, where the wave function of the universe has separate parts, one inside the bounded region and one outside the region. And I'm going to try and persuade you that that freedom is not there in a theory of quantum gravity. I'll also try and describe how, if you believe the extrapolate dictionary in ADS-CFT, hello, is there a question? Then such a picture is already something that you would have guessed in ADS-CFT, but I'm going to try and establish it independently for asymptotically anti-de Sitter spacetimes. The new result, though, that I'm going to try and emphasize is to establish a picture of this sort for four-dimensional asymptotically flat spacetimes. I should say a little bit about the philosophy of this talk and the way in which I'm going to proceed. So my idea is going to be to only use semi-classical considerations, but then I'm going to supplement some observations I make about the semi-classical theory of gravity with what I think are reasonable assumptions about the full theory of quantum gravity, and I'll outline these in detail as I go along. This picture that, once you specify the wave function of the universe everywhere outside a region, you don't have any freedom inside, has immediate implications for black holes. And one of the implications is that you shouldn't think in black holes or when black holes evaporate in terms of quantum information going into the black hole and quantum information coming out of the black hole, but rather in a theory of quantum gravity, one should recognize that information is always outside the black hole. And this has a specific quantitative implication. And the quantitative implication is that if one looks at the von Neumann entropy of a segment of future null infinity that includes the pass boundary of future null infinity, then this von Neumann entropy is trivial and it's not given by the oft-discussed page curve.
So, sorry, Suvrat, can I interrupt, or should we keep the questions till the end? I don't know what format you would like.
Whatever you like. I haven't substantiated any statement yet, but please go ahead.
I know, but it doesn't stop me from asking you. But let's take the case of asymptotically flat spacetime, Suvrat. Can't we talk about an S matrix that relates the in state at scri minus with the S matrix at scri plus, with the state at scri plus? And in that sense, isn't there a notion of something going in and something coming out? And couldn't we say that the information question is whether the S matrix is unitary or not?
Sorry. So the S matrix, whether the S matrix is unitary, I'm going to assume the S matrix is unitary. When I talk about information coming out, the question is if you take a segment on a future null infinity, and as you extend that segment from its past boundary towards its future boundary, so as you extend it towards time like infinity, do you get more information or not? The naive picture is you have an observer who lives on future null infinity and makes observations over a longer and longer segment of future null infinity. And the naive picture is that that observer gets more and more information as that segment becomes longer. And I'm going to try and explain that that's not the case, that the information is already contained at the past boundary of future null infinity. Now you're right that there is another description of this Hilbert space, which is in terms of past, I minus, scribe minus.
Right.
And then there is a unitary map between scribe minus and scribe plus, which is given by the S matrix. But as far as the quantum information of the state is concerned, that exists both on scribe minus and on scribe plus independently. And then there's an interesting dynamical question about how one Hilbert space is mapped to the other, but I'm not going to say so much about that.
Okay.
What I'm going to talk about is, given that their quantum information exists already on future null infinity, how do you extract that quantum information?
Okay. Okay.
You could ask a similar question on past null infinity.
Okay. Now I understand. Thanks for that. But just to say sorry, and then we go ahead. I mean, the information puzzle can be stated even, I mean, is a meaningful thing, right, in the theory of gravity, because it's a statement about relating the description on scribe minus to scribe plus.
One could phrase it in different ways. In this talk, I'm going to actually, I'm not going to say so much about unitarity. I'm going to assume the theory is unitary. But when one speaks about the von Neumann entropy or the page curve, that page curve generally makes reference only to future null infinity.
That's true.
You take future null infinity and you try and define a state in a segment of future null infinity. And then you ask, what is the entanglement entropy of that state? And what I'm going to argue is that the entanglement entropy of that state is going to be trivial. But you're right, you could ask other questions about dynamics, about which I won't say so much in this talk.
Yes. Thank you. Thank you.
Okay, so thank you for that question. So that was, I just summarized for you the introduction and the main messages that I wanted to give. Let me give you an outline of how I hope to proceed in this talk. The way I'm going to proceed in this talk is I'm actually going to spend a fair amount of time trying to describe how this picture of quantum information and quantum gravity works in asymptotically anti-de Sitter spacetimes. The reason for that is not because thinking about asymptotically anti-de Sitter spacetimes gives us a fundamentally new result, but because almost all the technical issues that already arise in the case of ADS, which is a more familiar setting for many of us to examine these phenomena. And so I'm going to spend, that's section 2 of the talk, on which I'm going to spend a fair amount of time. And then it'll be easy for me to generalize when I come to asymptotically flat spacetimes and point out how similar results hold in asymptotically flat spacetimes, with some caveats that I'll come to when we reach there. And then in the last part of the talk, I'm going to try and describe the implications for the information paradox, which we already briefly discussed. Okay, so as promised, let me start by describing how quantum information is localized in quantum gravity and asymptotically anti-de Sitter space. So I'm going to consider a spacetime that's asymptotically globally anti-de Sitter. So just to set up conventions, we have an SD minus 1, we have a radial and a time direction. And then, of course, I'm going to allow the metric to fluctuate, but the fluctuations of the metric are said to be normalizable near the boundary of anti-de Sitter space, and that's given by the boundary conditions that you see on your screen. It tells you that in a certain gauge where you set HR mu equal to 0, then the Hij components have to die off at least as fast as R to the 2 minus D. There could be other dynamical fields in the theory, and for them as well, we will choose normalizable boundary conditions. Now, the first question you would like to ask in the semi-classical theory is a question of what are the good physical observables in the theory. And now the physical observables in gravity are those that are invariant under small diffeomorphisms, because small diffeomorphisms are the gauge transformations of this theory. And immediately you find that you can construct an interesting class of physical observables, and those physical observables are given just by the boundary values of the metric and these other fluctuating fields as you go towards the boundary. So these are bulk observables, but you take the boundary limit of these bulk observables, you strip off the leading R dependence, and then whatever you get is an interesting physical observable. So you see, for instance, the boundary value of the metric gives you some observable that I'll call Tij, which is labeled by a point in the sphere and a point in time. And then if you had a scalar field, its boundary value would give you another physical observable that's denoted here by O, which is again labeled by a point in the sphere and a time quant. Now, just one statement about the notation. Those of course, from ADS-CFT, we know that this Tij is what in the conformal field theory is going to become the stress tensor, but I'm not going to assume ADS-CFT here. The notation is suggestive, but it doesn't mean I'm assuming already that there's an ADS-CFT correspondence. Now, what I'm going to be interested in is the algebra of these boundary observables. So this is a standard thing we do in quantum field theory. We have some set of operators, and then we multiply those operators in all possible ways to give us a bigger set of observables. So previously I described this boundary observable Tij, and now I could consider all possible polynomials and all possible functions of this Tij, and that would give me an algebra. Of course, I also need to include maybe the O's and whatever other boundary values I have, and that will give me an algebra that I'll call a boundary. Now, it's very important that I'm not going to start off by considering observables at all points of time. Rather, I'm going to start off by looking at the set of all polynomials in these boundary operators that live in the time band 0 to epsilon. So on your screen, you see a figure, and that figure, there's a little very thin red time band, almost looks like a single line. And the observables that live on that red time band are what I will call a boundary. Okay? So naively, and indeed in a local quantum field theory, this is just a small subset of all the observables that exist in the theory, but I'm going to try and tell you that in quantum gravity, the picture is very different.
So, sorry, Suvrat, this came up in the morning also. I'm a little confused.
Yes.
If you take just one instant of time,
yes.
at least let's assume ADS-CFT for the moment.
Yes.
If you take one instant of time and take all observables at that instant of time in the boundary theory, then you've got the entire algebra of observables, right? Including the Hamiltonian, and
yes.
then evolving it in some small time interval doesn't add to the elements of the algebra.
Yes, if you assume ADS-CFT, that's correct, but I don't want to assume ADS-CFT because when we go to flat space, we won't have an ADS-CFT dictionary ready-made for us. And so, as I said, the philosophy of this talk is I'm going to start by just looking at semi-classical aspects of the theory, and then I need to show that all quantum information is contained in this set of observables. So from the starting point where I'm starting at, this is just a small subset of observables that lives at all times. And in fact, the first argument I'm going to try and make is already from semi-classical considerations, supplemented with reasonable assumptions about the UV theory, and without assuming an ADS-CFT correspondence, you can already argue that this algebra contains all information.
I see. So just to make sure, are you then taking on the boundary, your A boundary is what, if we had ADS-CFT, we would say call only the stress tensor. Is that the point?
No, if I had ADS-CFT, then you're right that this would involve the set of all boundary operators at one time, which is the set of all operators.
So then,
if you assume ADS-CFT, this is the set of all operators. But in the semi-classical theory, naively, it's not the set of all operators. And what I want to prove is that indeed, this already has all information about the theory. You can think of this as trying to argue from the semi-classical viewpoint for holography. You're trying to argue for the origins of holography.
But Suvrat, I didn't understand, and I'm sorry to slow you down. What operators you are keeping in the semi-classical description in a context where you had ADS-CFT, you're only keeping some operators, then I gather.
No, in the context when I have ADS-CFT, it'll be all operators. Even in this context, at the end of the discussion, I'm going to argue it will be all operators. But I started off with the stress tensor and with, say, other boundary values. And now I multiply them together in all possible ways. So I consider arbitrary polynomials of these boundary values of bulk fields. That is the set of operators I'm starting off with.
Is this just a half BPS operator semi-classically?
No. There's no supersymmetry here, so I don't need supersymmetry. So
but if you look at ADS5 crosses 5, that would be the half BPS operators if you just look at supergravity level.
Yes, but then I'll multiply them together in all possible ways. So my polynomials will not preserve any supersymmetry anymore. You're right that my generators belong to the half BPS sector. But then if you notice here, you also have T into T. And I'll also consider T into T into T and T into T into T. So when I look at the set of all polynomials I get from these generators, I'm not going to preserve any supersymmetry anymore.
And how are you going to renormalize this when they come together?
Well, these operators right now are at separated points. But this is a question of how you define, the von Neumann algebra in a quantum field theory, an interacting quantum field theory. For now, these operators are just always at distinct points.
Thanks. Okay, please go on. Thank you.
Okay. So now the statement I want to make is as follows. The first statement, which we already discussed, the statement is as follows. I'm going to try and claim that purely from semi-classical considerations supplemented with some UV assumptions, if two bulk states are distinct, then they can already be distinguished by observables in this algebra that I call A boundary. So in particular, on your screen, you see two kinds of wave functions of the universe, one which is just some smooth wave function, the other which has a blue bump in the middle. And I'm going to try and say that whether the blue bump exists or not is something that can be discerned from the set of observables in A boundary. And once again, I would like to emphasize that you could have thought of a theory without gravity in asymptotically anti-de Sitter space, and then this statement would just have been false. You could still have defined this A boundary, and then the operators that created the blue bump would commute with all operators on this little red band on which A boundary lives. And so there's no way you would be able to tell whether or not the blue bump exists. And what I'm going to try and argue is that in a theory of quantum gravity, you can tell whether the blue bump exists or not. In particular, you can tell everything about the state from observables in A boundary. So you could think of this as an argument for why at least this aspect of holography is already implicit in a careful examination of semi-classical gravity. Okay, so as I said, as I described already, the philosophy is going to be that I'm going to make some careful examination of the semi-classical theory, and then at various points I'm going to assume that some property holds in the UV theory as well. So let me start with an observation about the semi-classical theory of quantum gravity in asymptotically anti-de Sitter space. The first observation you make when you quantize the theory is that the vacuum in an asymptotically global ADS spacetime is unique, and it's separated by a gap from the lowest excited state. So in the lowest graviton, for instance, has an energy D in ADS units. If you have some massive field, that field has the lowest excitation has an energy delta in ADS units. Now, the assumption that I'll need to make for the full theory of quantum gravity is that the vacuum in this full theory of quantum gravity, whatever it is, remains unique. So you see this blue state at the bottom of the graph, and the assumption is that even though the energies and precise energy levels of various states might get corrected, this vacuum will remain unique in the full theory. Okay, the second assumption, the second observation about the semi-classical theory is the following. In canonical quantum gravity, there's a very unusual feature, and that is that the Hamiltonian of the theory is a boundary term. Now, this is a direct result of imposing invariance under small diffeomorphisms on the wave function of the universe. And that tells you that if you wanted to determine the energy of the state is obtained just by taking the boundary value of the metric and integrating it on the sphere. And in some sense, this is not so surprising because this is something that we already knew from Gauss's law. It's the fact that the energy can be obtained by looking at the far away fall off of the metric. Now, it's a fact about the semi-classical theory that provided you regulate the theory, a question that already came up, provided you regulate the theory in a manner that respects diffeomorphism invariance, the Hamiltonian will continue to remain a boundary term because, as I said, the fact that it is a boundary term is a direct result of just imposing invariance under small diffeomorphisms. Now, I do not want to assume that this semi-classical Hamiltonian is the full Hamiltonian of the theory. Okay? I don't want to assume that. But what I will need to assume is that the vacuum of the semi-classical Hamiltonian coincides with the vacuum of the full theory, and the semi-classical Hamiltonian remains a positive operator. So this is an assumption about low energy physics in the full theory, and it's the statement that from the semi-classical theory, if you know that the subleading fall off of the metric is exactly as it is in just empty anti-de Sitter space, then you've correctly identified the vacuum. And the statement that this H remains a positive operator is a statement that you can't hide energy in quantum gravity. You can't hide energy from infinity in quantum gravity. So this is a restricted assumption. I want to emphasize once again, I'm not assuming that the Hamiltonian of the full theory is given by the semi-classical operator, but the assumption I'm making is a low energy assumption. It's that the vacuum is correctly identified by the semi-classical operator.
Sorry, Suvrat,
yes.
I'm really sorry for interrupting you so many times, but I don't understand exactly what you mean by the word semi-classical here. Can you just, in the context where there is a CFT dual, can you tell me more precisely what is the semi-classical approximation you have in mind? And when you say the Hamiltonian may not be as obtained from the fall off may not be the full. What did you mean?
In the context where you have a CFT, and if you assume the extrapolate dictionary, this is kind of a trivial statement because this fall off of the metric becomes the stress tensor, and then you integrate the stress tensor and you just get the Hamiltonian of the CFT. So in the context when you assume an ADS CFT correspondence, this is kind of a trivial statement. The question about whether this operator which you get from the metric is the full Hamiltonian or not is a question of whether you trust, at what accuracy do you trust the extrapolate dictionary? Do you trust it to exponential accuracy when you look at high energy microstates or not? So in the context where you assume that you already have an ADS CFT correspondence, this is not such a strong statement. But I want to emphasize that in all these early slides, I'm not starting off assuming that we have an ADS CFT correspondence. One way to think about this is, if you forget what we learned in the past 20 years and go back and we had a conversation with Wheeler and DeWitt, could we convince them that gravity in ADS was holographic or not? I mean, if you know ADS CFT, then a lot of this is going to be rather obvious, and then the new thing will be when we come to flat space.
Yeah, sure. No, but just to, sorry, and then you should go on. What exactly do you mean by semi-classical? Just to understand.
Very good. So what I mean is that I'm not making any assumptions about the UV structure of the theory. So what I mean is that you started off with the quantum field theory on anti-de Sitter space, and then you canonically quantized that theory. You found that you had some wave functions which obeyed some Wheeler-DeWitt equation. On that Wheeler-DeWitt equation, you found those wave functions and various operators evolved with this boundary Hamiltonian. And I'm not assuming beyond the assumptions that I'm stating the detailed structure of the ultraviolet theory.
I see. So maybe by semi-classical, you partly mean keep the low energy modes, including gravitons, etc., with some kind of a UV cutoff, then try to quantize the theory and deal.
But we know that program will fail, and that you don't expect to get a consistent UV theory. Mm-hmm. But by quantizing the low energy gravitons, you make certain observations about the low energy theory. Mm-hmm. And then I'm making some extrapolations, like this extrapolation on the screen is one extrapolation about the UV theory. And then the claim is that if you make those extrapolations, then that is sufficient to argue for this property of quantum information.
Okay. Thank you.
So I'm making some observations about low energy physics, and then I'm extrapolating them to the UV.
Okay.
So this is one extrapolation, that this low energy metric, for instance, can identify the vacuum.
I see. Okay. Thank you.
Okay. Now, since this low energy operator H that I described manifestly belongs to what I call the boundary algebra, because it's just the integral of one of these metric operators in the sphere. Now, the standard property of operator algebras is that if an operator belongs to an algebra, then all its spectral projectors also belong to the algebra. In particular, the spectral projector I'm going to be interested in is the projector on the vacuum. And by the assumption we just made, and in fact by assumption 1, this operator P omega is a one-dimensional projector, which is an element of this boundary algebra. And this is just a property you see from the low energy theory. And I'm assuming that it's a property that will continue to hold in the full theory of quantum gravity. Okay, our third assumption I need to make is about the Hilbert space within which I formulate the theory. So I'm going to formulate the theory in the following Hilbert space. Let's say we start with the vacuum in the far past, and then we excite it by acting with boundary operators at arbitrary times. So I want to emphasize that in this slide, these boundary operators are not restricted to the small time band 0 to epsilon, but rather they can live at all possible times. So the physical statement here is we start with the vacuum in the far past, and then we throw in stuff from the boundary, and then we get what we get. And that is the space of states within which we are working. Now, why is it a good thing to restrict to this set of states? It's a good thing to restrict to this set of states because this Hilbert space is manifestly closed under time evolution. You see that this is the case because if you evolve with the Hamiltonian of the full theory, you just juggle these time coordinates that you see on the screen around. And so just unitarity cannot force us to go beyond this Hilbert space. Just time evolution doesn't take you to any new states beyond the states you already have here. The second reason it's a good assumption to formulate the theory in this Hilbert space is that this Hilbert space is quite large. In particular, it includes all kinds of interesting black holes that can be formed from collapse. So this is going to be my third assumption, that there's, that the full theory can be formulated in this Hilbert space. Now, I emphasize.
Sorry, Suvrat, I'm really sorry, but what have you then left out? That is, you have not left out what we would call the very high anomalous dimension operators. Is that? I'm sorry, I keep using ADS-CFT language, but I'm just trying to make sure.
In this Hilbert space, what have I left out?
Yeah.
In this Hilbert space, this assumption is made to ensure that, sometimes people say you might have some states that can never be formed from collapse. You could describe some of these so-called bags of gold states, for example, which are black holes with some FRW universe in the interior. And then the question is, does holography work for those kinds of states? So those are states where you just write down some wave function in the bulk, but you never form it from collapse. This assumption is meant to exclude those kinds of states. Once again, in the CFT, this is a trivial assumption. It's a statement, you get it immediately by the state operator map. You start with the vacuum, you act on it with all possible operators at all possible times, and of course, you'll get all states in the theory.
Right,
so in ADS-CFT, this is a trivial assumption.
I see. No, I thought because you're working in a low energy theory, that's partly what you mean by semi-classical.
Yes, indeed. But when I formulate this Hilbert space, I would like to include all possible polynomials. So you're right. I'll need a UV theory to be able to make sense of what this means. But in the end, this will also include black hole microstates. It's important for me that this will include black holes.
So, okay.
Because I'm going to include all possible polynomials.
Okay. Yeah. Thank you.
Okay.
So sorry, now, I also.
Yes.
So I'm a bit confused because you're assuming that the projection to the grounded state is also a member of the algebra.
Yes.
But it seems to me that this projection is a minimal projection. So basically, you're assuming that your algebra is a type 1 algebra, which we know is not the type of algebra correct for the.
In the theory on ADS, you do have a type 1 algebra, right? I have to say, because you have a discrete set of states. You have a vacuum, you have a single excited state, but there is a one-dimensional state which is the vacuum, and you can project onto that. But that's something that we know from. Yeah, but it's
also quantum field theory, which is a type 3.
Well, I mean, this is just it's just a statement of vacuum as a unique state. So I mean, if that's what you mean, right? If you have one-dimensional projector, you have a vacuum which is a unique state. One way to think of this is you have the quantum. If you think of the CFT, you've quantized the theory on the sphere, and I'm looking at the full algebra. I'm looking at the algebra of all operators on the boundary, and that that it's a type 1 algebra because you manifestly have a vacuum which is separated by a gap from other states. The only question is, how do you have a one-dimensional projector, right? Do I understand correctly?
Yes.
But you do have a one-dimensional projector because there's a unique vacuum. And the unique vacuum is separated. I mean, it's not like the vacuum in a massless QFT where you have excitations that are arbitrarily close to that vacuum. You have a vacuum and then there's a gap. This will not be the case when we come to flat space, but in global ADS,
thank you.
Okay. So now I emphasized on the previous slide that this set of operators I was acting with lived at all times. But now I want to point out, I want to prove an intermediate result, which is that in fact, if you just acted with this boundary algebra, which is a set of operators that lives between time 0 to epsilon, you would effectively generate the same Hilbert space. More precisely, any vector in this Hilbert space that I called H previously can be approximated arbitrarily well by a vector in this space that I'm calling H prime, which is the action of the boundary algebra, which means operators in 0 to epsilon on the vacuum. Okay, so how do we prove this result?
Just a second. I think we have a question from Nirmalya. Nirmalya, can you go ahead and ask your question?
Yeah, sorry. So can you hear me?
Yeah.
So the question was, the full Hamiltonian is an operator in this Hilbert space that you defined?
The full Hamiltonian is an operator, yes.
So we know the action of the full Hamiltonian on these states. Is that correct?
Yes, because they just evolve, full Hamiltonian just generates time evolution. So it takes you from one state to another state.
Okay, thanks.
Here, right? So these states are generated by acting with operators at a given value of time on the vacuum. So the full Hamiltonian just changes the values of t. Is that good?
Thanks.
Yeah. Okay. I'm not going to need that in detail. I just needed that to argue that this Hilbert space was closed under unitary evolution. Okay. So so now I want to argue that the same Hilbert space you would get by acting with operators in the time band 0 to epsilon on the vacuum. How do we make that argument? Well, let's prove it by contradiction. Let's say there was some vector in the bigger Hilbert space, but which could not be generated by the action of operators between 0 to epsilon. If so, then when you consider this function f of ti that appears on your screen, which is the inner product of psi with this product of t's, ti's, localized in the time 0 to epsilon, then this function f of t must be 0 whenever the ti's are in 0 to epsilon. But now we can insert a complete set of energy eigenstates in the middle. And when you insert a complete set of energy eigenstates, and if you assume the positivity of energy of the full Hamiltonian, then you will see that this function f of ti is analytic when it is extended in the upper half plane. Now, if you have such a function, and if you know that it vanishes for ti real in some domain 0 to epsilon, then you can argue that it must vanish for all real ti, just standard theorem in complex analysis. But we know that this function f of ti cannot vanish for all real ti because the state psi was generated by the action of some ti's at some values of time. So this f of ti must be non-zero at least when these generators take the value of time that was used to generate the state psi. And therefore, we've reached a contradiction, and therefore we cannot have any state that is orthogonal to all states that are generated by acting with operators in the band 0 to epsilon. Okay. So this says that in fact, all states in the Hilbert space can also be written or can at least be approximated arbitrarily well by starting with operators in this boundary algebra and by acting on the vacuum. Okay. Now I want to show a much stronger result, which is that any two distinct states can be distinguished by an element of the boundary algebra. I would like to emphasize that this previous result I showed didn't even rely on gravity. It's a result that would even hold in a quantum field theory. And in fact, it often happens that you can generate all vectors in a Hilbert space by acting with some small element of the algebra or some small algebra. But it's a much stronger statement to say you can distinguish any two distinct states in the Hilbert space by an element of the algebra, which is the statement that I now want to establish and which will crucially use gravity. So the statement is as follows. Say that there are two states which are unequal. Now, if these states are unequal, then there must exist, by definition, some operator to which these states endow distinct expectation values. What I want to show is that such an operator must belong to the boundary algebra. So the proof is as follows. Let's take this operator that distinguishes the states and let's expand them out. Let's expand this operator out in some basis, which is the sum over n and m. And now you can write every state that appears in this basis as the action of an element of the boundary algebra, which I called xn and xm on the vacuum. That gives rise to this first equation that you see on the screen. And this expansion exists by the previous proof I gave, which is that all states can be generated by acting with the boundary algebra on the vacuum. That's the first equation. But now notice that there is an operator that appears in the middle, which is ket omega bra omega, which is the projector on the vacuum. But the projector on the vacuum also belongs to the boundary algebra in a theory of gravity by one of the assumptions that we made previously. And therefore, you arrive at the second equation, which tells you that x is just a sum over xn, p omega, xm dagger. But an algebra is closed under products and taking linear combinations. And therefore, this operator x must belong to the boundary algebra. And that proves, subject to the low energy observations and extrapolations that we made, that any two states psi1 and psi2 which are distinguishable are also distinguishable by operators in this boundary algebra. So let me just recap. I assumed that the vacuum remains unique in global ADS, about which we already had some discussion. I assumed that the vacuum can be identified through a boundary Hamiltonian. And I assumed that we can restrict to states produced by exciting this vacuum from the boundary. All these three assumptions were assumptions about the full theory of quantum gravity, but they came by extrapolating simple observations about the low energy theory. Subject to these assumptions, we were able to show that all information about the bulk is contained in an infinitesimal time interval on the asymptotic boundary.
Hi, can I ask something?
Yeah, is there a question?
Yeah, so where did you use gravity in the last statement?
The statement was, it was in two. You see, if it was the fact that the vacuum could be identified through a boundary Hamiltonian, which is unique to gravity. I'm going to emphasize that a little bit more in the next few slides.
So I could have the statement thrown for any QFT where you could identify the vacuum from the boundary.
There is no other QFT where you can identify the vacuum through a boundary Hamiltonian. You mean bulk QFT?
Yeah.
I don't know any other bulk QFT where you could identify the vacuum through a boundary Hamiltonian.
Okay, thanks.
I'll emphasize that a little bit more in the next few slides. Okay, so this, of course, if you know ADS-CFT, is a simple, and that's the reason I emphasize this derivation first, is a simple consequence of ADS-CFT. But what I wanted to emphasize, in a sense, was a canonical view on this observation about the fact that quantum information in the theory of quantum gravity is stored near the asymptotic boundary. Okay, as the question previously was, what is the importance of gravity? Of course, this whole argument would not have made any sense without gravity. For instance, you might have said, well, let me think about a non-gravitational gauge theory. And in that case as well, certain boundary charges, charges are boundary terms. But you can never distinguish, you can never determine the full details of a state from the boundary. For instance, think of a state psi, which is the state psi on the left, and think of the state produced by taking psi and acting on it with e to the I trace of f squared, localized at the point 0, where 0 is some point in the middle of ADS. Now you see that this operator e to the I trace of f squared 0 is a unitary operator which commutes with all elements of the boundary algebra in a non-gravitational theory. And so these two states cannot be distinguished by any boundary measurement without gravity on the little red time band. So gravity was very crucial to make this argument. Not only gravity, it's important that its classical gravity would not have been sufficient, and it was important that we had to invoke quantum gravity. And the reason is, a very simple counterexample. In classical gravity, you could just think of two different classical configurations, one being a compact configuration, this little red dot that you see on the left, one being a more diffuse configuration of dust, both being completely spherically symmetric. And then if you try to make observations in this brown time band, this A boundary, in the classical theory, the metric is completely identical in both cases because it's just given by the Schwarzschild metric outside. And there's no way in the classical theory you can distinguish whether you're in the state in the left or the state in the right. And one way to understand this is that in the classical theory, you only get to measure the expectation value of the Hamiltonian, but in quantum mechanics, you get access to higher moments of the Hamiltonian as well. And that's very important and gives you much more information than you get in the classical theory. Finally, I would like to emphasize that some of these arguments might have seemed like some abstract mumbo jumbo. I'm making some arguments about operator algebras, and I'm trying to argue that everything exists in some operator algebra near the boundary. But in fact, you can verify these arguments concretely in perturbation theory. In particular, let me give you the following. You could have given me the following challenge. You could have said, let's take the vacuum and let's now act on the vacuum with some, say, dynamical scalar field. Let's smear it a little bit about the center of ADS, and let's act on the vacuum with this smeared field. This is the state psi. Now, can you tell me what was the shape of the smearing function f of r by making observations just near the boundary of ADS? And the answer is actually yes. And the answer is you need to measure a 2-point function, and the specific 2-point function you need to measure is a 2-point function that involves the metric and an insertion of the same scalar field. You can compute this 2-point function in perturbation theory. It's a simple computation. And you find that this 2-point function reduces to a 2-point function of the field itself smeared with this function f of r. And once again, if you know this right-hand side, this 2-point function for a small range of time, which remember was important for me, I had my boundary algebra for a small range of time, you can completely reconstruct this function f of r. So these are not abstract arguments. Concretely, by measuring some correlation functions near the boundary, you can show how you can determine information about the bulk. Of course, as the bulk state becomes more and more complicated, the bulk state I have here is a particularly simple state. It's like a one-particle state. As the bulk state becomes more and more complicated, I need to measure higher and higher point correlators near the boundary to determine information about the bulk. But in some cases, you can also play this trick about black holes. So here is an example about how you can use perturbation theory to look behind black holes. So the example is as follows. let's say you start with the black hole microstate, which has a very thin spread in energies. So it's almost an energy eigenstate. And then you take this black hole microstate and you excite it so as to produce an excitation behind the horizon, which is what you see on your screen. So you have a shell which is produced just behind the horizon of the black hole, once again by an excitation of a simple unitary of the kind that I described previously. You take some field, you smear it a little, and you act with that unitary on the original black hole microstate. And then you would ask me, well, now this excitation is behind the horizon. Can you determine the form of the excitation by measuring some correlators on the boundary? And the answer is yes. You need to measure a slightly more complicated correlator, but once again, it's a 2-point function of the metric and an insertion of the same field. And you can show once again that you can use that to determine what this function f of r is. I emphasize that this was a very special set of microstates. It was in almost energy eigenstates excited in a particular fashion, but classically these excitations were behind the horizon, and what this shows is that you can determine their form by measuring correlators outside the horizon. And this gives you one concrete example in perturbation theory of how you can look behind the horizon in a straightforward way.
Sorry, Suvrat, this
Yes.
last example
Yes.
was what I was thinking of bringing up. If you can just go back one
Yes.
slide,
Yes.
because it has me really confused.
Yes.
Outside of the horizon, of course, nothing changes if you excite the shell inside.
Classically, nothing changes.
Classically, nothing changes.
Yes.
But I mean, you are figuring out stuff on the boundary through the fall off of various classical fields, or what are you doing?
No, it's the action of this, it's a 2-point function. So it's not just looking at the fall-offs of various classical fields. I have to measure a 2-point correlation function. So there's a factor of, there's a quantum correlator. And, the way this HTT acts is it acts like the Hamiltonian.
Sorry, let me just stop you there, because you're not assuming ADS-CFT. So this is a state in the bulk?
Yes. It's a state in the bulk, and then I have to measure a 2-point function of the metric, and it's a correlation function of the metric and the same scalar field.
Sorry, on what space-like slice is the state defined? Is it defined on a space-like slice that crosses the horizon?
Yes.
Or that doesn't cross the horizon?
The space-like slice crosses the horizon. You have to take a nice slice that crosses the horizon, and now you have a horizon, and then you think of so you have an original state. Now you excite it in this manner, and the challenge is, can you determine what was the form of the excitation? In the semi-classical theory, when you want, of course, you have to take a space-like slice which has complete description. So it's a nice slice.
So then, I mean,
yes.
But at various points in this equation here, you have HTT infinity omega.
Yeah.
That
so
infinity refers to what?
Refers
R.
to radial infinity, near the boundary, near r equal to infinity.
So,
and I have dropped some various factors of r that you would need. This HTT should have had various factors of r to the d and so on, which I have not displayed.
right, but it seemed to me, therefore, were you not making a point in your intermediate formula, and I might have misunderstood it, that by measuring a 2-point correlator, but with both HTT and phi at infinity, you would be able to tell whether you had a shell inside the horizon or not?
That is correct. So you take the state and you compute only a 2-point correlator at infinity. The previous question you asked me was, how is the state defined? So of course, in the theory, you would need, if you wanted to define the state in the semi-classical theory, I just wanted to say that you would try and define the state on some slice in the semi-classical theory. But what I'm computing here is just a correlator near the boundary. So it's the picture that I tried to emphasize in the beginning, that if you give me the form of the wave function of the universe everywhere near the boundary, I don't have any freedom really left in the bulk. So by measuring details of the wave function near the boundary, I'm going to determine also what the form of the wave function in the bulk is. And in this case, it's one example of how that would work.
When you say you should go on, but when you say you can verify this in perturbation theory, what exactly do you mean? What is the precise calculation? But you can tell me later.
It's this calculation. It's a computation. It's the first to the second line. So you compute a 2-point function of the metric and the scalar field. That reduces, that you can show, it turns into a computation of the 2-point function of the scalar field itself. This 2-point function you can compute in the original black hole background. And you can show that if you know this 2-point function for a small range of t's, you can recalculate what f of r is.
Okay, so just to understand, you semi-classically quantize gravitons
Yes.
and your scalar about the black hole background, with and without the shell, let's say,
yes,
or let's say with the shell for the state psi.
There's the caveat. The caveat is that you need to ensure that your original microstate has a very thin spread of energies. So, but yes, please go on. Yes.
So among the various black hole microstates,
yes, that's
how
good.
do you ensure that semi-classically, I thought you just start with this given geometry, we all know, and
Correct.
then you put in a little bit of a wiggle for the graviton, your HTT, and for phi, you quantize the theory and you take a 2-point function.
Correct. So
I mean, if you normally did it, one way to do it is you would quantize everything in Rindler coordinates, which never cross the horizon, and then you would not see any effect of the shell.
No. You would see an effect of the shell, because remember, you would when you put the shell in, there's a Gauss law that you have to preserve. So you have to be careful about the zero mode, and you also have to be careful about the zero mode when you quantize the theory. So you're right that to do this calculation is a subtle calculation, because usually we are not careful about the fluctuations of the zero mode. And that's the reason yes.
Yeah, you should go on, but later, I mean, explain to me how in a semi-classical calculation you would put in the constraint that you're choosing a particular microstate or one with small energy, as opposed to just the black hole background.
It's the fact that the wave function has to also have information about the spread in the zero mode of of the zero mode of H. And this, so you have to be careful that you start with a wave function that has a small spread in the zero mode. So you would have to put that in the wave function that you started with, and that's an important consideration for this specific thing to work. Let me say another thing actually. Let's say we started in ADS-CFT. Let me say we are in ADS-CFT. You could still ask physically the same question. You could still consider these states in the CFT, these states, the energy eigenstate E and the state psi. And you have a family of states psi which are labeled by f of r. And now I could say, measure a 2-point function in the bulk, and let's say we assume ADS-CFT so that everything is well defined. Measure a 2-point function in the bulk but near the boundary, and tell me, can you look behind the horizon and determine what the form of f is? Would that be a setup which would make you happier?
So sorry. Well, go on, I think, with your talk, because I didn't fully understand. I mean, what is strange about this is it seems to indicate that information from inside the horizon is being seen by correlators way out at infinity.
Correct.
Right?
Correct.
And normally we don't think that can happen. The light cone would prevent that. And in semi-classical approximation, well, okay, maybe the light cone fluctuates a bit, but it shouldn't fluctuate drastically.
No,
so
much more.
To reconcile the two. Sorry.
Let's do the same thing about the vacuum. If you don't like this, here's another example. In this example, this is an excitation which was made around ADS r equal to 0 and t equal to 0. And the correlator I'm measuring is at r equal to infinity and near t equal to 0.
Okay.
So you have precisely the same objection. And now this is a completely well-defined calculation in the semi-classical theory. I don't even need to worry about ensuring the zero mode has a small spread. I just start with the vacuum. I quantize the theory about the vacuum, and then I have this set of states which are excited with something deep in the interior, which is space-like separated to things that are far away, and I have to determine what the form of the excitation is. And the answer is you can determine. And the reason is actually that in gravity, these operators at space-like separation don't commute. You have some small commutators, and that's why you see a factor of G Newton, and those are the commutators that one is exploiting to extract this information. So this question about the light cone structure you could have asked even previously, and you see that the light cone structure is indeed violated. You're making an excitation deep in the interior, and you're trying to detect if it exists or not at the same time by measuring correlators near the boundary.
And are you saying then that in the theory of gravity, you don't have our usual notion of causality, that information spreads, I don't know, arbitrarily fast outside the light cone?
Yeah, so you have to be much more careful about the notion of causality that you have. This correlator is a small correlator because it's suppressed by a factor of G Newton. So in the limit, when you took G Newton to 0, you would recover the usual notions of causality. But so it's not that this correlate. I mean, if I didn't have this factor, I would be in trouble. So I do need a non-gravitational limit, which we do have here. And then indeed, it is the case that in the theory of gravity, information is localized in very strange ways, as you see in this example here. So I mean, it's important, as you pointed out, to have a non-gravitational limit. Because in the world around us, we have causality to an excellent approximation, and that's preserved by these commutators. These are small effects. So this 2-point function far away develops a small factor. But if you look carefully at that small factor, you can determine what's happening deep in the interior. And indeed, that's the point that I would like to emphasize, that you can't modify the interior without modifying the boundary. And it's true that the boundary modifications are small. You have to look carefully, but they do exist, and they're set by the constraints.
Thank you. Thanks a lot. Sorry for that.
Okay.
Sorry.
Okay. Yes. More questions? Are there more questions?
Yeah. So can I just make a very small clarification?
Yes.
Yeah. So, this story that you're telling us about the shell inside the horizon,
Yes,
that doesn't have an obvious Euclidean analog, does it?
No, it does not have a Euclidean analog. I don't know how to state in Euclidean theory.
So you're saying that the boundary theory, or the set of operators that you're describing, it's only a good description for a Lorentzian case. You cannot take that theory and put it on. You cannot think about a Euclidean continuation of that theory. Are you saying that?
No, I'm not saying there's not a Euclidean continuation. There's a Euclidean continuation, but this setup you're asking, where you think of an excitation behind the horizon, I don't know how to frame that in Euclidean language in a nice way. That doesn't mean there's no Euclidean continuation. I mean, this is just a standard problem that the moment you continue in the Euclidean theory, the things cap off at the horizon. So to talk about the interior, you need a Lorentzian description.
Suvrat, you must go on, but I'll just ask the question and you answer later. Are you saying the following? If a bomb went off inside a black hole,
Yes.
I was sitting outside and was able to measure correlators up to order G Newton,
Yes.
I would know the bomb went off?
Yes.
I'm not sure I believe that, but
okay.
But
it's a surprising result, and you're right to be surprised and to emphasize the surprising aspect.
Okay.
Let me say another thing in which let me give you another thing which might make you less skeptical. You see, the fact is that if when the bomb went off, the thing is that someone had to have gone in from outside to have set off the bomb. And another way, you see, the computation I showed you is just a 2-point computation, but the thing is, you could think of it as taking advantage of the fact that this person who went in left some imprint on the space-time, which is what you exploited. But once again, I would urge you not to think only about black holes. You could think about just an ordinary space-time. Mm-hmm. So let's say we happen to cover the perimeter of the institute with very fine detectors, and then a bomb goes off in the middle of the institute. Can we determine immediately that the bomb has gone off? And the answer is yes. And to make you less skeptical, the reason it's yes is because the person who set off the bomb had to have crossed the perimeter and gone inside, and so you already knew in a sense that the bomb was going to go off. So it's not, you can't really use this to violate causality. You can't use it to set up superluminal communication. Is this clear?
I thought you were saying yes in that at least. I'm sorry, I go back to a black hole just because it's striking, but yes. You're right, we could do it another. I thought you were saying even without a black hole, if you did something deep in the inside, you would more or less instantly know about it outside.
You would, but yes, but you see, you still don't have a protocol for superluminal communication, because to set up a protocol for superluminal communication, you need a setup where the wave functions are distinct in the interior and the same outside. And then you ask, if I changed it one way or the other way, would I know outside? In this case, the wave function outside already completely determines what's happening inside.
I see.
So, it's the fact that if you wanted to set off a bomb inside the institute or inside a black hole, you would already have modified the wave function outside in such a way that by those correlators, you would know what was going to happen inside.
Okay, I see.
It's not like you have the option of setting off the bomb or not setting off the bomb.
I see. Okay. Thank you for that clarification.
Okay.
Sorry for the interruption.
Yeah, okay.
Can I ask also, I mean, I think it's similar, but
yes.
somewhat differently phrased.
Yes.
So would you need to have information about the operators, which usually would be dual to string states in ADS-CFT, to be able to determine something that happened very deep in the interior from the perspective of the boundary?
Yeah, for very simple states of the kind I described, yes, that's true. So for the way, as I said, it's simplest to just think about the vacuum, and I can ask, you make an excitation deep in the interior, but you give me time only from 0 to epsilon. Can you determine by simple operators which simple state you're in? And the answer is yes. Of course, if you have two complicated microstates and you tell me, I just give you some simple 2-point functions, can you tell me which microstate you're in? The answer is no. Because to determine the microstate in full detail, I need very complicated correlators. The examples I picked were cherry-picked because they were simple states, which in a local QFT you would not have been able to distinguish, but I wanted to point out that in these simple states, you can measure simple correlators on the boundary, including the kind that you see in string theory. I was just measuring a graviton and a scalar field, and you would be able to determine which state you're in.
But then from this perspective, is it fair to say that you would need, in a sense, to have back the entire string theory, including all its UV structure, in order to be able to determine something that happened in the deep interior, and just the semi-classical information is not sufficient?
No, so if you wanted to determine everything that happens in the deep interior, including the full details of the microstate, then I agree that you would need the full details of the boundary theory. But in some examples, if I give you a prior that the state is either the vacuum or the vacuum excited with a simple operator, or the other prior I gave you, it's an energy eigenstate excited with a simple unitary, then I can already determine by simple operators which one it is. But I had to give you a prior. But if you ask me which approximate energy eigenstate is it, then I would need the full details of the UV theory.
No, I mean, I agree for simple states, you want need the entire information, but just for the, in matter of principle, because in a sense your previous slides were in a sense it was just a matter of principle. I mean,
I agree.
You can determine everything from the boundary, but to determine everything from the boundary, you need to know the information about all operators, and that takes you back to the full string theory.
I agree that if you to really determine everything, you would need a full UV theory of gravity. What I wanted to emphasize was that even without knowing the detailed structure of that string theory, you would still be able to argue that quantum information is localized near the boundary. And you're right that if you really gave me two different microstates to determine the details of that microstate, I would need details of the full UV theory, including the yes. Okay. Thank you. Okay, so we spent a lot of time on ADS, so hopefully I can go through the flat space discussion relatively fast. Yes.
Question. So, Suvrat, the Hilbert space that you described,
yes,
was formed by operators acting near the boundary.
Yes.
So, how does the previous state fit into that Hilbert space?
Formed by operators, you would form that. Well, one way you could think of the vacuum thing is you have some HKLL kind of description of the bulk field, and then you act on it, the original state with this description. For the excitation behind the horizon, you would need some mirror operator description, but its action on the vacuum, once again, you can write in terms of simple operators. Once you act on it on a given energy eigenstate, you don't need the mirrors anymore. The action is described in terms of a simple generalized free fields. For the vacuum, you would use some HKLL kind of map to describe the state.
I see.
Okay. Okay, so thank you for those questions. So hopefully, so I'm now going to go on to flat space, where the results are going to be new, even though I'm going to use the same techniques, but I'm now going to try and deduce, in a sense, how I think information is stored holographically and asymptotically flat spacetimes. There's been a lot of work on this, of course, going back many years, starting with the work of Debord and Solodukin, most arguments of Marolf, which actually are similar in some ways to the discussions that I'm describing here, and also more recent work by Strominger and others. So I'm going to spend some time just reviewing some aspects of the semi-classical theory on flat space, of gravity on flat space, and then I'll describe once again what are the generalizations I need to make about the UV theory, and then describe once again what I know about how information is stored. Okay, so there are several ways in which flat space differs from ADS. In particular, the vacuum is infinitely degenerate in 4 dimensions. I'm going to talk about 4-dimensional flat spacetimes. And null infinity only has information about massless particles. And another peculiarity, which may become important as we go along, is that the standard way of taking the boundary limit in flat space drops all interactions, unlike in ADS-CFT, where the boundary theory remains interacting. And nevertheless, I'm going to try and persuade you that the technique that we have still generalizes very nicely to 4D asymptotically flat spacetimes. Okay. So I'm going to consider a 4-dimensional asymptotically flat spacetime Once again, we need to set up, this spacetime is asymptotically Minkowski, but then there are some subleading fall-offs of the metric. These subleading fall-offs are parameterized in by what's called a CAB, which is called the shear. And then we often speak in terms of the derivative of the shear, which is called the Bondi news. And then there is this important variable, which is MB, which is the Bondi mass aspect. And these are just different components of the metric near null infinity. And once again, you have similar fall-offs for matter fields. Now, there's a nice thing that happens on future null infinity is that if you start with a full nonlinear theory of gravity, this nonlinear theory trivializes on null infinity. And you can compute some exact commutation relations and constraints for this nonlinear theory, and those are the ones that appear on your screen. And the details are not important right now for us, but what I want to emphasize is that these are just exact commutators in the full nonlinear theory. They don't rely on making a quadratic approximation to the theory, and that's because as you go towards null infinity, you tend to drop all interactions. Okay. Now, one other thing that we knew for a time, but has been emphasized a lot in the recent literature, is that the theory in flat space has an infinite number of supertranslation charges. And the supertranslation charges can be divided into what are called soft and hard pieces. The supertranslation charges can be written as the integral of this Bondi mass aspect near the past boundary of future null infinity, which is what you see here denoted as u equal to minus infinity. So u is the retarded time, and u equal to minus infinity is the past boundary. And then you can rewrite it in terms of some hard and soft charges. And the relevance of these hard and soft charges is that the vacuum of the theory is infinitely degenerate, and it's given, it's completely specified once you specify for me the values of these soft charges. And on top of each soft vacuum, you can build a Fock space by acting with these news operators and these matter operators that I showed on the previous slide. Now, what I call the full Hilbert space of massless particles is precisely this infinite direct sum where you start with all these possible vacua and you excite it with all possible news operators and all possible matter operators on asymptotic null infinity. This is what we would usually call in S-matrix description the outspace of massless particles. All the statements I'm going to make in the rest of this talk are going to be confined to this Hilbert space.
Sorry,
Okay.
Suvrat,
Yes.
sorry to interrupt. And I'm sorry to be so poorly versed about these developments. But if you just go back to your previous, the sum labeled by S is not different super selection sectors.
No.
You can go from one to the other.
That's right. You can go from one to the other.
Okay, thank you.
Okay, so now let's look at, I also need to define once again these algebras of asymptotic operators. So once again, I look at the set of asymptotic operators on some segment of null infinity. This segment has to have a small thickness, a u and u plus epsilon, which is important for me as it was important in ADS. And then I look at the set of all polynomials in asymptotic operators in a segment of null infinity. And if I'm looking at some segment somewhere in the middle of null infinity, I'll call that algebra A of u. And then if I'm looking at the algebra near the past boundary of null infinity, which is what you see as the red, little red thing where the mouse cursor is, that I'll call A of minus infinity. So A of minus infinity, which will be particularly important, is a set of all functions of operators on null infinity with the u coordinate being very close to minus infinity. Okay. So now, as we did in ADS, I'm going to assume that some aspects of the semi-classical theory carry over to the full theory. And I'm going to emphasize it by making some very weak and very reasonable assumptions only about the low energy theory, only about low energy assumptions. We already obtained interesting results about how quantum information is stored in flat space. And by making stronger assumptions, we can obtain stronger results about how quantum information is stored. And the discussion is going to be very parallel to ADS. And so I'm going to go through it slightly fast. Okay, so here is the first result I'd like to establish. Any two distinct states in the space of massless particles can be distinguished just by observables in A minus infinity. So in particular, I said that you got the space of massless particles by acting with all possible excitations on all of scribe plus on the vacuum. But I'm going to say you can distinguish which state you're in just by observations in this little red patch which lives near the past boundary of future null infinity. Okay, that's going to be the first result which I'd like to establish, which is the statement that information is stored holographically in asymptotically flat spacetimes. Okay, what are the assumptions I'm going to need? The first assumption is that the vacua in the full theory are labeled by operators near the past boundary of future null infinity. Now, this is manifestly true in the semi-classical theory because all vacua are labeled by their supertranslation charges. If there were additional charges in the full theory of quantum gravity, whatever that is, this assumption is okay with that, provided these additional charges are also defined near the past boundary of future null infinity. The second assumption I'm going to need to make is that operators that map the space of vacua back to itself, the question that Sandeep just asked, if you go from one sector to the other sector, that these operators are also contained in the algebra near the past boundary of future null infinity. Once again, this is something you can just check explicitly by constructing such operators in the low energy theory. And so in the low energy theory, this assumption is true. And I'm going to assume it holds in the full theory of quantum gravity. And the reason I think this is a good assumption is because this is an assumption only about low energy vacuum physics. And so all I'm assuming about the full theory is not some detailed structure of the UV theory, but just the fact that the vacuum physics remains the same as it does in the low energy theory. And that's why I think this is a good assumption. Then the argument proceeds just the way as it did in ADS. Using the positivity of the full Hamiltonian, you can first show that you can generate all elements of this massless Hilbert space by acting with operators in A minus infinity on these different vacuum sectors. And I won't repeat the argument because it again uses analyticity properties that work just the way as the ones I described previously. Then, by the assumption I made, the operators that map one vacuum to another also live in this algebra A minus infinity. So now I don't have a projector onto the vacuum. There was a question previously about whether you had a type 1 algebra or not. So this is not a type 1 algebra. There's no one-dimensional vacuum, but the projectors that take you from one vacuum to the other live in this A minus infinity by the assumption I made about vacuum physics, which can be checked explicitly in the low energy theory. And then you can show that any operator that maps this massless Hilbert space back to itself, once again, you expand it out in a complete basis of states. You write every state as the action of some operator in A minus infinity on one vacuum. And then you take the intermediate ket S bra S prime and you write it as one of these transition operators. And now everything on this slide lives in A minus infinity. And therefore, the product and the linear combination of all of them also lives in A minus infinity. And this already proves, using these very weak assumptions just about vacuum physics, that all information about massless particles is contained near the past boundary of future null infinity.
Suvrat, Rajesh.
Yeah.
Just the previous slide, where you said using the same analyticity. So in the ADS, you use the fact that you had this band, and therefore there was this. You use this edge of the wedge theorem. So what is the analog here? Sorry, I'm not familiar with
the fact that the full Hamiltonian generates evolution also in retarded time for operators in future null infinity. So now we generated the full Hilbert space by acting with operators that were labeled by different values of the retarded time on the different vacua. The full Hamiltonian translates you in this retarded time U. If you assume that the full Hamiltonian is positive and there's some complete set of energy eigenstates you can insert, and once again you can show that these functions that you have are analytic when you continue the differences of retarded time in the upper half plane. And then you can argue that if you have a state which can be generated by the action of some operators which have some values of retarded time between minus infinity to infinity, that same state can also be generated by the action of operators which have retarded time from minus infinity to minus 1 by epsilon.
So you're saying there is analyticity in this on the time variable on the, but it's a null variable, right? So
yes, it's a null variable. But there's still some analytic property. I mean, yes, it's a null variable, but we still have this analytic property. I mean, it's just using the fact that the Hamiltonian generates translations in this.
So you can go to the upper half plane or whatever.
That's right. That's right. When you do the LSZ formula, this is what I mean. You Fourier transform along this null variable and you pull up the energy. So it's
Okay. Thanks.
Yeah.
Sorry, Suvrat, just, yeah, in this, I know I'm really sorry I've interrupted you so many times, but just to understand this very counterintuitive result, let me pose the following and then you say again. You have a spherical ball of stuff, maybe a star, right?
Yes.
And so at least naively, as you yourself said, by Birkhoff's theorem, you have very little information, it would seem, outside.
Yes.
And at some time t equal to 0, the ball explodes or something, photons, gravitons come streaming out,
yes.
and they reach Sky plus, but
yes.
they reach Sky plus at some fairly late time, depending
yes.
on when the ball exploded.
Yes.
Nevertheless, you're saying sitting near a minus infinity or whatever, you know, the bottom end,
yes.
You would have known much before.
Yes.
Everything about this.
Yes. So in this case, let me simplify your example, and then we can do it in perturbation theory. As I said,
okay.
I don't have the example on this slide, but you do the following. Let's take a shock wave. So the shock wave is going to come and hit us at null infinity near u equal to 0.
Okay.
And the shock wave is created by starting with one of these soft vacua and acting on it with e to the I, some smeared function of f. So you could create this shock wave at past null infinity if you like, and then now it will come and hit us at future null infinity at some point.
Okay.
And now you can ask me, can I determine what the form of the shock wave is just by making observations in this little red band?
Right.
And the answer is yes. You need to measure the 2-point function of the Bondi mass and the news. So let's say it's just a gravitational shock wave. So you need to measure once again a 2-point function of the Bondi mass and the news, like the 2-point function I showed in ADS. Let me go back a few slides to that. Apologies for this. It's here. Except this is an ADS example. Now instead of HTT, I need to measure MB, and instead of phi, I need to measure the news operator. It's actually given in our paper. The formula is given in our paper. And you can check for this kind of a shock wave by measuring this 2-point function. You can determine the form of the shock wave in A minus infinity.
I see.
Explicitly.
And so the point is, as you've been emphasizing, but let me ask, is that there are sort of, so to say, the analog of long tails, is
exactly.
it? On Sky plus.
Exactly.
And that somehow.
Exactly.
Let's see. Okay. Okay. Thank you.
In the classical theory, of course, you would not be able to, but in the quantum theory, you can. Okay.
So this positivity of the Hamiltonian, I mean, in classical general relativity, you have a positivity of the Hamiltonian.
Yes.
I thought that was violated even at one loop, right? No.
The full Hamiltonian, I'm going to have to assume is positive. I mean, it's bounded below at least. I'm going to have to assume that the full Hamiltonian of the theory is bounded below. Otherwise, the theory wouldn't make sense. So I'm not talking about, there's no local, it's not a local energy. It's the energy integrated on the full sphere.
Full sphere.
So the full Hamiltonian
capturing
right, it's just a total energy. So total energy I'm going to have to assume is positive. If the total energy is not positive, if it's not bounded below, then none of this will work.
Of course, as you know, I mean, yeah, it's probably reasonable to assume, and probably a quantum theory should have this, but I mean, it's not an obvious thing in gravity. I mean, even the classical theorem was, of course, not obvious. But,
yeah, correct. That's right. So I'm going to need to assume that in the full theory of gravity, we have this positivity property.
Yeah,
otherwise,
I guess otherwise you would have a sig theory. You wouldn't have a. Okay.
That's right. Okay. Okay. The second result I want to prove is going to make slightly stronger assumptions, and I'm going to argue that the information actually has a nested structure in future null infinity. In that any information that's available in a cut of null infinity, like the blue cut, is also available to a cut to its past, which is the red cut that I have. For this, I'm going to need slightly stronger assumptions. And this goes as follows. See, in the semi-classical theory, I pointed out previously, there were some commutation relations you could work out between the Bondi mass and the operators in null infinity. And what those commutation relations tell you is that the Bondi mass acts like the Hamiltonian for operators to its future, but not for operators to its past. Now, the assumption is that this commutator is going to remain exact in the full theory, or at least is going to receive very specific kinds of corrections. Now, you might say that's a very bad assumption because you computed some commutator in the low energy theory, and now you want to assume that it holds in the full theory. And indeed, it's a somewhat strong assumption, but not as strong as you might think because of the fact that I emphasized previously. Even in the full nonlinear theory, this commutator actually depends only on the quadratic terms in the effective action. And that's because the standard way of taking the limit to null infinity drops all interaction terms. The way you take the boundary conditions, all high order terms just drop out and do not enter into the computation of this commutator. And so it's not unreasonable to assume that this commutator is something that might stay uncorrected in the full theory. And it's not as unreasonable an assumption because at least in the effective action into all orders in perturbation theory, it would be the case that this commutator would not be modified. If you make this assumption that this Bondi mass, and you compute its commutator in the low energy theory, and you assume that this commutator is uncorrected, and as I argued, it's not as bad an assumption as you might think, then you can clearly see that you can use this Bondi mass just to evolve operators from the red slice to the blue slice, because the Bondi mass in the red slice continues to act like the Hamiltonian for any operator to its future, and therefore you just act with these operators e to the IMU and e to the minus IMU, and you can evolve information from the red slice to the blue slice. On the other hand, and unlike anti-de Sitter space, you can't go back. You're not able to go from the blue slice back to the red slice because this Bondi mass does not act like the Hamiltonian for operators to its past. So this gives you a slightly more intricate picture of how quantum information is stored in null infinity. It's not like ADS where the same information exists at all times on the boundary, but rather that you have a lossy structure. You have the most information near the past boundary of future null infinity, and then you have less and less information as you go inside. One way to think about this intuitively is to think of future null infinity as the boundary of a space-like Cauchy slice, and then this past boundary is like the outermost point of that slice, and as you go towards what is marked here as the future, it's like going inside, and as I pointed out, as you go inside, you have all information about what's inside, but not about what's outside, and so in a sense, this is establishing that picture of nested quantum information. Okay, let me just recap the results that I showed, starting with very weak assumptions just about vacuum physics, namely that the vacua are identifiable by charges near the pass boundary and that operators near the pass boundary can map one vacuum to the other. I argued that all information about massless excitations is available near the pass boundary of future null infinity. By making a stronger assumption about the commutators and constraints from asymptotic quantization, receiving only specific corrections, which I justified based on the fact that the way you take the limit tends to drop all higher order terms in the effective action, you can argue that the information on any cut of scribe plus is also available in any earlier cut. And let me point out that the result 1 is a subset of result 2, because if you agree with result 2 that information on any cut of scribe plus is available in a past cut, then it follows that all information is available on the past most cut, which is the cut near the past boundary of scribe plus. But of course, result 2 requires stronger assumptions. And if you don't want to make those stronger assumptions, then we can live with result 1. Okay. Last part of the talk, I'll try and go through it fast. I know we're running a little short of time.
Sorry,
yeah,
just to ask you, if you go to one of your slides where you have scribe plus, I mean, let's say there's a photon which or graviton which reaches, you know, way up towards the very far along scribe plus.
Yes.
And you were trying to detect it already in some way by sitting at the bottom.
Yes.
Is there a sense in which you have to be more and more precise in your measurements as, you know, if the point where the photon or graviton hits is further and further along?
Yes, I think there's a power law fall off. It's 1 by delta U. I forget the exact power now.
It's only power. It's only a power law.
Yes, it's only a power law on null infinity. We have only massless particles, so there's no scale. So it's all power law follows.
Thank you.
Yes. Okay. Any other questions? Okay. If not, let me go to the last part of the talk. Now I'm mostly done with the technical stuff. So now I want to talk a little bit about the information paradox. You know, attention is often focused in the information paradox. The way it's often phrased is we ask, you know, how does information, we have a star, the star, you know, died, formed a black hole, and then the black hole evaporated to give you photons. Photons obey Planck distribution, so it looks like information is lost. And if it's not lost, how does information come out of the black hole? And this is indeed the way we tend to think about local physics. But if, as I've been trying to say, this information that you might have thought comes out in later parts of future null infinity is already available near the pass boundary. And another way of saying this is that the information is already always outside. And so perhaps this is not the right way to frame questions about black hole information. Let me try and describe some of the quantitative implications of this statement in terms of the entanglement entropy. So one way in which people discuss black hole information is by discussing the von Neumann entropy of a segment of Scri plus, like this red solid segment you see on the left part on the figure on your screen. Now, Page analyzed the average entropy of one subsystem when you split a big system into two parts. And he argued, and it's true for us when you do such a splitting, that this average entropy obeys the curve that you see on the right part of your screen. And Page argued that this is indeed what should happen for black holes, because you think of black hole evaporation as a big black hole breaking up into small parts, where the radiation gradually comes and hits you on future null infinity. And so you have access to larger and larger parts of the original system. And therefore, he argued that the von Neumann entropy on null infinity will obey the Page curve. And this is indeed a common expectation. However, if you accept result 1, then there's an immediate corollary, which is very easy to prove. I won't prove it, but it should be intuitively obvious that in fact, the von Neumann entropy of any segment that includes minus infinity of Scri plus is independent of its upper limit. And the reason for that is that, as I tried to argue, the information is already available in an infinitesimal interval of minus infinity. And therefore, by extending the segment higher and higher, you get no further information about the state. You can prove this more formally, but as I said, it's intuitively clear if you accept result 1. If you also accept result 2, which is that any information on a cut is available to a past cut, then this tells you that you take any segment U2 and U1, then this von Neumann entropy of the segment is independent of the upper limit of the segment and only depends on its lower limit. So let me just summarize the results about von Neumann entropy, and I'll go back to the Page curve. This is how these results fit in the broader framework. You make some assumptions about vacuum physics, which are the assumptions on the left. It tells you that information is contained near the pass boundary of future null infinity. This tells you directly that the von Neumann entropy of excitations on a segment that goes up to U but includes minus infinity is independent of this number U. You make stronger assumptions. They tell you that information on any cut is available to the past of that cut, and it tells you the von Neumann entropy of a segment in the middle doesn't care about the upper limit. Okay, so what's a more realistic Page curve? So more realistic Page curve for this segment is therefore just a flat curve. It tells you that if you take this red segment that goes from minus infinity up to some point U, and you compute its fine-grained von Neumann entropy, you would just get a constant. The reason I have a finite constant and not a 0 is because in our analysis, I didn't keep track of massive particles which live near time like infinity in the conventional description. And so there is some entanglement of the massless particles with the massive particles, and that entanglement will just always remain whatever observations you make on null infinity. But barring that, there is no additional information that you get as you extend this U from minus infinity towards plus infinity. Okay.
Sorry,
Yes.
Suvrat,
Yes.
just to ask you, and I can ask you
Yes.
again later,
Yes.
because you say since it's based on incorrect assumptions about factorization of the Hilbert space.
Yes.
Just to ask you, I mean, in gauge theories, which I understand a little better,
Yes.
also the Hilbert space doesn't factorize because of Gauss's law, etc.
Yes.
Are you saying there's a much more complicated version of this at Scri plus due to various soft charges?
Much more complicated. You know, in gauge theories, as I said, you still, the factorization is the lack of factorization is not that bad, because there is still a sense in which you can localize quantum information in some region by acting with a gauge invariant operator.
Right.
But in gravity, as I've been trying to argue, the lack of factorization is much more serious. You can't localize quantum information at all. So it's a much more serious problem than gauge theories. And in fact, the argument is if you computed the full fine-grained entropy of the algebra, you would just get something trivial. So it's much more serious than gauge theories.
But I was trying to ask whether, is it in some, are the charges associated with these generators, etc., are they like gauge transformations, and that is resulting in super selection sectors, or they're analog for some region? Is it like that, or what is it?
No, it's not super selection sectors. It's the fact that all elements of the algebra already live in the small algebra near minus infinity. Now, there are no operators in this bigger algebra that goes up to U that don't already live in A minus infinity, which is what I tried to argue previously. If you computed the relative entropy all the way up to U, there is no state that you would be able to distinguish that you couldn't already have distinguished near A minus infinity. And that's why the entanglement entropy is trivial. Let me say it another way. The essential difference between gauge theories and gravity is that you have this notion of positivity, and you can project onto a unique state using A minus, using the charges, which you can never do in gauge theories.
True.
And
okay,
that's
no, thank you. I'll ask one more again. You can postpone all this, but I mean, physically, if you're sitting near the bottom of Scribe Plus, whatever it's called, and you say you have all the information of the entire history that is to unfold. Is it a statement in some vague way that you need to know arbitrarily soft stuff?
Very good. I'm going to come to that in the next slide. So can I just postpone it for 1 minute? I'll come to that for a minute.
Sure.
Yeah. So let me just come to that in the slide after this. Okay. So you might have said about the page curve, and I'll come to Sandeep's question. You might have said, well, this trivial page curve is very surprising. I've never seen anything like it. But in fact, you have seen something like it. And you've seen something like it in the following setting. Consider a small black hole that forms and evaporates in ADS. Now, let's say you make arbitrarily accurate measurements near the boundary of ADS. We know from ADS CFT the boundary is always in a pure state. So if you computed the full von Neumann entropy of all these operators, you would always get 0. So it's not like this von Neumann entropy obeys some page curve where the state first looks kind of impure and then looks pure. It just always looks pure. Now, coming to Sandeep's question, you might say, well, wait. There's a sense in which there's some hierarchy of complexity that appears. But, and you might have said, and maybe once you take into account the fact that you can't make arbitrarily complicated measurements, you see a page curve. But you see a crude estimate just for the ADS CFT example, which is familiar, tells you that that is not the case. I'll go back to this example of a small black hole forming and evaporating in anti-de Sitter space. Before the black hole formed, which was at time t1, which you see on your screen, information is easy to recover. You can easily determine using low point correlators what the form of the state is. After the black hole is formed, which is at time t2 in this cartoon, information is hard to recover because the horizon is formed. And you can estimate how hard it is to determine what the microstate is. And a crude estimate tells you that you require about S point correlators to determine the form of the microstate at time t2. But after the black hole evaporates at time t3 and emerges into Hawking radiation, you still require S point correlators because the information is stored in e to the minus S correlations in the Hawking quanta. So while it is true that to obtain all information about the microstate at T2, you need very accurate observations, that's a crude estimate suggests that's the same level of accuracy that you need at the later time T3. So you could either say that I'm limited in my accuracy and I can't make measurements in quantum gravity of S point correlators and I can only measure 2 or 3 point correlators. But then the entropy that you would get would be a coarse grain entropy, and that would obey the standard Hawking law. It would just keep increasing because the state would look like you have some thermal photons that are coming and hitting the boundary. Or you could say, well, I do have the ability to measure arbitrarily high point correlators or at least S point correlators. And if you did that, then you would find that the fine grained entropy was always 0. And it's not clear that there is any intermediate regime where the entropy first goes up and comes down. So while it is true, same in asymptotically flat space, that to know information about everything that's going to unfold on future null infinity, you need to make very accurate observations near the past boundary of future null infinity. You also need to make very accurate observations to extract information from the Hawking radiation. And it's not clear that there's any hierarchy of difficulty between these two difficulties. Does that answer your question, Sandeep?
No, thank you for that clarification. But Suvrat, just to ask, suppose you had put a cutoff, and this is not precise, please excuse me, but a cutoff on some analog of the frequency, so you're cutting off very soft stuff. I mean, we can talk about it later. I was just wondering, in that way of cutting off rather than S point, there might be some sense. But maybe I'm wrong. I haven't thought about it. But I was just wondering, it seems to be very soft stuff that is carrying all the information already at the bottom of Scribe Plus.
No, it's not very soft actually. There's some information, very soft stuff, which is the entanglement between the hard and soft degrees of freedom. So if you define a state on Scribe Plus, part of the entanglement entropy lives on, in the fact that you have some hard excitations on top of these different vacua. And to determine that, you need these very soft modes. But that complexity would also exist as you made observations on all of Scribe Plus. It's not.
Okay. All right. I need to internalize this. Then go ahead, please. Thank you.
Okay. So now, let me just say a few more things about the information paradox. You see, people say, well, you had this increasing curve in the previous slide. You had this entropy that was going up, and that was a semi-classical argument. And what is the error in that argument? In this way of looking at things, the error in that argument is kind of clear. This argument fails to account for the unusual localization of quantum information and quantum gravity that, as I've tried to argue, is already evident in the semi-classical picture. And if you try and make some assumptions about the UV theory, is an argument you can make in the UV theory as well. So from this perspective, this would be the error in Hawking's argument. It's the reason why this curve on the right-hand side gets translated into this curve at the bottom. Okay, I had a few more things, but in that view of time, maybe I'll skip through these things. And let me just end with some contact with the recent literature. I've tried to argue that the von Neumann entropy of black hole radiation is not described by the page curve. And in fact, this is the interesting aspect of gravity, which is that information is always outside. But I would now like to say in a few minutes that it is, of course, possible to change the question appropriately so that the answer becomes the page curve. Okay? How would you do that? If you wanted to get the page curve as an answer, what is the right question you should ask so that you get the page curve? To get the page curve, you need a setup in which the Hilbert space factorizes. And conceptually, the simplest setup to consider is this plasma ball solution of Shiraz, Ofer, and Toby Weisman that they now set up many years ago, 15 years ago. And the plasma ball solution is the following. You have some boundary theory, which extends infinitely in the transverse directions. You have some lump of the quark-gluon plasma, which is this region D. And then that lump of the quark-gluon plasma gradually dissipates into the confined phase, which is this region C. So gradually just dissipates into glue balls. In the bulk, this is dual to a black hole, which is localized in the transverse directions. You could now ask, what is the von Neumann entropy of the region C on the boundary? Now, the boundary is a gauge theory, but as Sandeep and others have described, there is a sense in which you can compute this von Neumann entropy, and you do believe that the Hilbert space factorizes. And so it's reasonable to expect that the entropy of this region C does obey the page curve in that it goes up and then it comes down. This is in fact similar to the recent derivations of the holographic page curve that have recently appeared in the literature. What you do there is you don't take a plasma ball because that's technically very hard to do, but rather you take a theory that describes the ADS black hole and you couple it to an auxiliary system, which is the bath. And then you compute the entropy of the bath. But this whole process can be viewed just by forgetting about gravity and just thinking of a non-gravitational theory, which was a theory that lives on the boundary, which is coupled to some bath. And of course, it is the case that then the entropy of the bath should obey a page curve because that falls squarely within Page's original derivation. But in terms of interpretation, I would say that the bath is not the radiation. Not only because the bath captures some regions inside the black hole, but most importantly, the bath misses some regions outside the horizon that lie between the horizon and the original boundary. And so that is also something that you would say is part of the radiation, which is not captured by the bath. So I would say when you compute the entropy of the bath, that's the entropy of the bath and not really the entropy of the radiation, because the bath misses some aspect of the radiation. This is another setup which is similar to the setup that was described previously. This is a setup where you take an SYK model or some quantum dot, you couple it to a two-dimensional conformal field theory, you compute the entropy, the von Neumann entropy of the red strips, and you find that it obeys this semi-page curve on the right-hand side. But this very crucially relies on gravity being non-dynamical where the red strips live. So gravity is non-dynamical in parts of the space, and that is what allows the Hilbert space to factorize and allows you to derive this result. In our world, where gravity is dynamical all the way, you would not expect to get this page curve, I would say, and rather you would expect to see the trivial page curve for this fine-grained entropy of these red strips. And I think it's incorrect to state that just because gravity is weak on the red slices, because these red slices are far away, that this entanglement entropy should obey the non-dynamical curve, and we can forget about the subtleties of lack of factorization and just assume that gravity is non-dynamical. In fact, as I've tried to emphasize, gravity localizes quantum information unusually, and neglecting this repeatedly leads to paradoxes, and I think it would lead us to an incorrect conclusion here as well. While this conclusion is valid when gravity is non-dynamical in this red region, I do not think it's valid when gravity is dynamic. Okay, so I'm done. Let me just conclude. As I tried to emphasize many times, an important principle in quantum gravity is that if you specify the wave function everywhere outside some region, you're left with no freedom inside that region. And this is an important aspect of how quantum information is stored, even when gravity is weak. This principle, I tried to argue, follows from semi-classical considerations supplemented with assumptions about the UV theory. In ADS, it leads us to a familiar result, which we already know, that all information is available in asymptotic operators, which we already knew from the extrapolate dictionary in ADS-CFT. In flat space, depending on how strong you make your assumptions, it tells you that information on future null infinity is also available near its past boundary, and information on any cut of null infinity is available in any past cut. In black holes, it argues that, it tells us that you shouldn't ask the question of how the information comes out. Rather, one should recognize that the information never goes in, and the page curve is trivial for the fine-grained entropy of black hole radiation. Okay, so that's all I had to say. I'm sorry for going over time. This is just a summary slide that outlines the assumptions I made in flat space and the results we had. So thank you very much for your patience and for listening. I'll stop here.
Okay, thanks, Suvrat. Do we have any more questions for Suvrat? We already had a few, but we can go on now.
Sorry, can I ask a question?
Yeah.
No, thank you very much, Suvrat. That's a really beautiful talk and really wonderful work. Just this is not very precise, but I mean, I do continue to feel that there might be a way in which you can make the original question still meaningful in your theory with gravity and radiation by thinking of the set of operators we have in mind that could, in some experimental way be conceivably used. Okay, and what I mean by that is the following. There is a sense in which if the Britannica gets thrown in to make a black hole, that information is extremely hard to recover sitting at infinity, long after the Britannica has fallen in and much before the radiation starts to build up. And what is the sense in which that information is very hard to recover? You say, at least I understand, not along space like infinity, but along past boundary of Scri plus, you say it's instantly available.
Yes.
But at least the fact that somebody, I agree, who's on a space-like slice, very far away from the black hole which is formed, somebody like that at least has a very hard time finding that information. Doesn't it suggest that it's very hard to recover sitting at the past boundary of Scri plus?
Yes, it's very hard to recover. It requires very accurate correlators, but I would like to emphasize it's also very hard to recover from the Hawking radiation. So you see, it's not like there is a simple hierarchy of complexity, that there is the person who's collecting the Hawking radiation has an easier job to do than this person who's sitting on the space-like slice far away. And that was the crude estimate that I made in ADS, that you could ask how much, what is the order of correlation functions that you need to determine this information very far away from the black hole, and the answer is S-point correlators measured up to accuracy e to the minus s. And then you could ask what is the complexity of measurements you need to measure to get it from the Hawking radiation, and the answer is again S-point correlators up to accuracy e to the minus s. This is not a very precise estimate. It might be that there's some intermediate scale of complexities which somehow makes it easier to get from Hawking radiation than from without Hawking radiation. But it's not so clear to me that such a regime exists. Let me give you another argument from statistical mechanics why I think such a regime shouldn't exist in any obvious way.
Sorry, Suvrat, please do, but I mean, before the black hole forms, you can do very easy measurements, as you said, right?
Yes.
Okay. And then after the black hole forms, although you say the information never went
Yes.
in, you have to do very difficult
Yes.
measurements. Is it just in terms of the S-point correlators?
I think so. You have to measure like S-point correlators, and that's a very difficult measurement because
that's certainly true.
And I think it's the same after it evaporates. Can I say, if you could think of this in the boundary theory, which might make this clearer. You see, think of a situation where you have some quark-gluon plasma that forms and then that evaporates into glue balls. You have two glue balls that come and they crash, they form some quark-gluon plasma, and then that eventually evaporates and dissipates into glue balls. And you're allowed to measure glue ball operators. Before the glue balls collapsed, before they crashed, you could measure like 2-point functions of glue ball operators and you would know what the form of the glue balls was. After they formed the quark-gluon plasma, it's quite hard to determine, to reconstruct what the glue balls were doing in the past. But you see, when the quark-gluon plasma is evaporated into many smaller glue balls, it's harder to determine what they were doing in the past because things only become more and more thermal. So it's always harder and harder to get back information about what happened in the past. I don't know of any setup in statistical mechanics where things thermalize and then things suddenly become easy, information suddenly becomes easier to recover. And this idea that the Hawking observer, or the observer who collects Hawking radiation at late times, would have an easier time recovering information would suggest that this is how the theory works, that somehow at late times it becomes less thermal. You're able to extract using lower point correlators the same information. So that's why I'm skeptical of the idea that the late time observer has an easier time than the earlier observer. Yeah. I mean, both of them have a hard job.
Okay, all right. Let's continue this offline. But just to say, I mean, the thing I'd like to understand is a lump of coal burning in a theory without gravity.
Yes.
In that situation,
yes.
Probably you would agree that as you march up along Scri+, you would get something like the page curve.
Absolutely, because you set a cutoff which doesn't involve M Planck. You see, this cutoff S crucially involves energy scale, M Planck divided by energy scale to the power d minus 2. In the case of the lump of coal, you would set a cutoff that depended on the number of particles of the coal, which would be much lower than this scale. Mm-hmm. And so it's clear that doing the quantum gravity measurement would again involve some number of correlators that scales with M Planck. But if you just have a lump of coal, or if you have 10 qubits that are evaporating, you just measure a 10-point correlator, and you don't need to make some Planck scale observations of how the metric was influenced by those qubits. That's much harder to do than just measuring the qubits directly. The key aspect in black holes is that the order of the correlator also involves M Planck. You're again measuring E by M Planck divided by E to the power d minus 2. So that's the difference between the black hole and the lump of coal, I think. In one case, there's a clear hierarchy of complexity. In the other case, I think there isn't. I mean, maybe there is, but it's not clear to me that there is.
Okay. Thank you. Thank you.
Hi, so I had a question.
Yeah.
Hi, Suvrat. Thanks for your talk. So, you mentioned that you were restricting to massless excitations,
yes.
the holographic description of massless excitations.
Yes.
So if you consider massive excitations, then is there a good reason to believe that the holographic description is again something localized to the past or future null infinity? Because, I mean, massive excitations would, like at late times, they move to the future time like infinity. So it might be that there is a description which is, the dual description is something which is localized, not to the past, but to the future.
Yeah, or maybe you need a union of the two. That would be one way of describing things. I think a better way, just a speculation, I think a better way might be you generalize the formalism of asymptotic quantization to thicken null infinity a little bit. And then if you thicken it, so you include also some parts of the radial direction, then you may be able to get information about massive particles already on a cut of null infinity. I mean, if you thicken it in the radial direction. But this is just a speculation. It may be, as you say, that the right description is a union of past boundary and future boundary. Maybe.
Okay.
I don't have anything more precise to say than what than this.
Thank you.
Do we have any other questions for Suvrat?
Okay, I guess not. Thank you everyone for sticking on.
Okay, yeah. Thanks, Suvrat, and thanks everyone for attending the talk and for sticking on for this discussion. If any of you guys want to continue asking some questions, informally, I'll stop the recording now and we can do that,
Sure.
or we can also break off.
Yeah, sure. Yeah, I'll just take along a little bit in case someone has other questions. Thank you very much for that.
Thanks.